Hey Algebra 2, welcome to this video. It's going to just take us through a little bit of our basics of working with logs. Before we get into logs, I want to start simple over here with these three numbers, 3, 6, and 18. And I want to show you that I can make two true statements using those three numbers. Here's my first one. 3 times 6 equals 18. Easy, right? Here's another true statement. 18 divided by 6 equals 3. All right? We might look at that and think about this as the multiplication form, and this is the division form. All right, I know I could make a couple more using multiplication and division, but let's just stop with those two. And now let's think about, with logs and exponentials, let's think about the numbers 2, 3, and 8. Here is an exponential statement using 2, 3, and 8. 2 to the third power equals 8. I think we all know that by now. Pretty simple to understand. 2 times 2 times 2 gives me 8. I would refer to 2 as the base and 3 as the exponent, right? So here it is in log form, that same statement. We keep the base the same, and we read this as a log with a base of 2 of 8 is going to equal, look at the piece we haven't used, log base 2 of 8 is going to equal 3. All right, that's essentially how logs work. So just a quick little review. I know some of you were getting this pretty good last week, but a little more practice doing some log evaluations. So we just did that first one. Log base 2 of 8 is equal to 3. And here we go. Let's look at log base 4 of 16. Well, we know that's going to equal some number. So you can also convert between log form and exponential form by thinking about this as, we could switch this over, like I was saying, 4, starting from the base, 4 to the x would equal 16. Well, we know that 4 squared is 16, so that means this x must really just equal 2. All right? So it's giving us exponents. Logs give us exponents. Logs give us exponents. Log base 5 of 625, if you know it or not, it's going to be 4. Log base 10 of 100,000 is going to be 5. All right? And these bottom four, you can try them in your calculator if you need to using the log base function. But this would be negative 2. This would be negative 4. That's where we start to get negative exponents. And then we also have rational exponents. Square root is the same thing as 1/2. Fifth root, well, that's a tough one because it's not a 3 and a 3. 3 to the what would give me fifth root of 9. 3 to the x gives me the fifth root of 9. I'm going to make that 9 into a 3 squared. Okay, that's like a 5, which is a 1/5. So I'm going to go with this all together equals 2/5. And if that's tough for you, that's okay. We'll get a little more practice next week. The other thing we did with logs is we looked at the graphs of them. All right, if this is the graph of an exponential in red, and I throw the line y equals x down here in green, here's what a log is going to look like. Pretty much symmetric across that line y equals x. So if we know about the domain, and I know some people who were in topics last week got to do this, we can't take the log of negative numbers. No negatives in logs. So we want to think about what's the smallest number I could put in there that will still be positive. Well, I could put in 0. 0 plus 5 is still 5. I could put in negative 1. Negative 1 plus 5 gets me positive 4. That's fine. So I can go into the negative realm. So these are kind of out as answers. How about negative 5? Negative 5. The negative 5 plus 5 would be 0 in there. Can I take the log of 0? And the answer lies here on the graph, where this is our asymptote. Okay, that's our asymptote there. So it actually cannot equal 0. Cannot equal 0. But now that I look at it a little bit closer, there's no equal to sign there. So we're perfect. That's our answer. All right. A graphing of a log. Yes, you could just do this in your calculator with the log base function. I can also do it without by looking at that point right there, 4, 1. That means if I take 4 and I plug it in for x, it's meant to give me a 1. And where's that going to happen? That's going to happen here on the fourth option. Log base 4 of 4 would equal 1. So that's my best answer. Here you go, question number 3. Which could represent the y-intercept of that function? Y-intercepts happen when x equals 0. I left that little note right there. Let's plug in a 0 for x. Well, that's nice and easy. Log base 2 of 32 minus 1. If you're getting good at evaluating logs, you will know that this just equals 5, and 5 minus 1 is 4 right there. Pretty easy. Last one I'm going to do, number 4. Which one is not in the domain? You could just plug in all these numbers and see which one gives you a negative or a 0. I think it's going to be 5. But here is the more algebraic way of doing it. We're going to need whatever expression is inside here, 10 minus 2x, excuse me. I need that to be greater than 0. If I subtract this 10, negative 2x needs to be greater than negative 10. Let's divide negative 2. When I divide an inequality by a negative number, it's going to flip to be x needs to be less than 5. Is 5 less than 5? It is not, so that's the problem. Negative 3 would work, 0 would work, and 4 would all work. Anyway, thanks so much for watching, guys. I hope that's a good little review on logs and working with them, and I will see you in class.